welcome back. Last time I finished by saying that today we would do integration by parts. And that was, of course, a lie. Well, I was at least mistaken. Yes, I already did integration by parts last time. I meant to say integration by partial fractions. So most of what I'm going to do today is about partial fractions. I'm hoping that that takes about an hour and a half, and that I have half an hour to do some trig-type integrals in preparation for next week's topic of trig substitutions. All right? So that's the game plan. Partial fractions for quite a while. Now, just to set the scene, we're continuing with topics of integration here, methods of solving integrals. Now, I'm not going to be spending any time on definite integrals, because as you know, most of the time to do a definite integral, you have to do the indefinite integral first, and then substitute in the bounds. That's pretty much the way. So let's just worry about indefinite integrals, then it's pretty easy to turn those into definite. Now, if you have a polynomial over a polynomial, P of x over Q of x. This is called a rational function inside there. Poly over poly is a rational function. The method of partial fractions is the normal tool you're going to want to use. Before I do this, though, let me just point out when you should not use partial fractions. Suppose you have some integral where the denominator's derivative is in the numerator. For example, (3x squared plus 10x over x cubed plus 5x squared plus 7), you might think, oh, it's a poly over poly, I'll do partial fractions. But if you notice that the derivative, 3x squared plus 10x, is exactly what's on the top. And you might remember from last time, we said, well, if the derivative of the bottom is on the top, it's just the log of the absolute value of the bottom. You can just write down the answer. Or you can use a substitution. Let t be x cubed plus 5x squared plus 7, and you'll find it works out, plus c. So this would also be true if I had a multiple of the derivative on the top. But that's a sort of miracle in a way. It's just miraculous. If I change the 10x, for example, to 9x, or just change these coefficients any way other than multiplying them by, say, 2 or a half or some constant number, then this wouldn't work. So it's just a sort of minor miracle, as I say, if the derivative of the denominator is on the numerator, in which case don't use partial fractions. Just use substitution, or the rule we did last week about logs. So that said, let's suppose that's not the case, which is true most of the time. What do you do? Well, what you do is you embark on a method. It's an algorithm. This stuff is not really pretty from a theoretical point of view. Part of it actually is, although I'm going to stay way, way away from that, I'm afraid. But actually, when it comes down to it, I'm going to teach you tonight how to be a computer and work these things out in the sort of way that a computer or a calculator that's smart enough can do in a fraction of a millisecond. But someone had to tell the computer how to do this. And you also may one day get stuck on a desert island without a computer, and your life may depend on your finding an integral of a rational function. That's pretty unlikely as well. But anyway, let's just play with it. Okay. So what I'm going to do is show you the steps that are involved in a sort of informal way first. Then what I'll do is I'll write them all down in a nice method. And then what we'll do is one big example that is about as hard as you could possibly expect, at least in Math 104, from a partial fractions question. So that's the game plan. Now, the way it works is this. We've got to do some algebra first. No calculus. We're just going to do some manipulations with polynomials and fractions and all that sort of stuff. And then we're going to see how to integrate things. So the calculus sort of comes at the end, or is the second half of the process. So without being too formal about the method, let's just sort of say that, well, okay, what we'd like to do is bust up our nasty partial fraction, say something like this, 5x squared plus x minus 3 over x squared minus 1. We'd like to bust up our nasty rational function into some smaller pieces which we can integrate one by one. And the first thing that I want you to think is nice is a sort of sense of balance. In my mind, this is balanced because the degree on the bottom is 3, but the degree on the top is only 2, which is less than 3. I kind of think, oh, well, the bottom's supporting the top without falling over. Here, this is no good because the degree of the top is equal to the degree of the bottom. The same would be true if the degree of the top was higher than the degree of the bottom. So the first step in the whole process is to say, is it balanced? Is the degree of the bottom bigger than the degree of the top? If it is, you're golden. You can ignore this whole first step. But otherwise, I'm afraid you've got to bust out a polynomial long division. Okay, so the first step is I notice that degree, I ask, is degree of the bottom bigger than the degree of the top? Alas, no. So divide. That's the sort of first thing to look at. That's what you want the bottom to be bigger than the top. If not, you have to divide. So in this case, as I say, the degrees are equal. Alas, we have to divide. So how do you do it? Well, whenever you do a long division, you have to put the numerator, imagine actually you wanted to do something like, 712 divided by 39. You'd say, how many times does 39 go into 712? Well, here we want to know how many times does x squared minus 1 go into 5x squared plus x minus 3. So this is bringing us back to high school days, hopefully. X squared goes into 5x squared 5 times. Now multiply the 5 by the x squared minus 1, and you get 5x squared minus 5x. No, minus 5. I was right the first time, in my mind anyway. So 5x squared minus 5. And you subtract, and you're going to get x plus 2. Minus 3 minus 5 is 2. So it's actually remainder x plus 2, because now the degree of the remainder is less than the degree of the denominator. So there's no way you can keep going. How many times does x squared minus 1 go into x plus 2? It doesn't. So what does this mean? This means that 5x squared plus x minus 3 over x squared minus 1 is equal to 5, that's the quotient, plus the remainder over the original denominator. Okay, it seems a little bit weird, but it's actually no different from this sort of behavior here. Actually, if you multiply through by x squared minus 1, you can check this. You see, you'll get 5x squared minus 5 plus x plus 2, which is exactly 5x squared plus x minus 3. You'll have the plus 2 and the minus 5, and you still have the x, and then you get the 5x squared. So you can always check these things after you've done it to make sure that you did it right. Okay, so what does that do for us? Well, now if you whack an integral and a dx in front of all of this stuff, you will see we've already busted it up a little bit. The first integral is just 5x. Don't forget the integral of a constant. It's not just the constant. It has an x in front. Plus a different integral, which in this case looks simpler than the original. The question is not so much whether it's simpler, but look at the degree. Now the degree of the top is 1, which is less than the degree of the bottom, 2. So now we're in the right situation, the more balanced situation, where the degree of the top is less than the degree of the bottom. So we're golden. Now, this has always got to work. This has always got to work if you don't screw up the division. See, the fact is, that by the definition of the division algorithm, the remainder has to have a lower degree than the original denominator. So you only have to do this once. You don't have to sort of do it over and over again to get the degree down little bit by little bit. No, it goes in one step. Okay? As I say, you really hope you don't have to do it, but if you have to do it, then you have to do it. Anyone have any questions about that first sort of preliminary step, as it were? Yes?
In the long division, what if you had 2x squared minus 1?
So 2x squared minus 1 here? Well,
You have to divide,
it would be...
x squared. No, just listen.
Yeah.
You have to divide x squared plus 2.
Okay, let me write this down as you're saying it. X squared plus 2?
Yeah. Divide this by
Oh, yeah.
2x squared. What I'm asking is if you write 5 and a half, basically. 5 plus half plus remainder.
So here, of course, I would say how many times is 2x squared, I'm sorry, how many times does x squared go into 2x squared? Are you trying to get a fraction up there? Is that what you're angling at?
Yeah.
So what you want is like a 5x squared plus 2. Okay, yeah, I mean, there's no need to stick in whole numbers here. If you've got 5x squared into 2x squared, how many times does that go? Well, you have to multiply this by 2/5.
So you would put a fraction up.
Oh, absolutely. Yeah. There's nothing about whole numbers that's important here. There can be any real numbers at all. All these coefficients can be real numbers. Okay? Etc. Any other questions about that? All right. Well, okay. Let's just say that no matter what your partial fraction, you've always inspected that the degree of the top is less than the degree of the bottom. And if not, you've done this division and you've gotten it to that stage. Okay? So that's the first sort of step. If you've done that, the next thing you want to do is factor the denominator. As I say, I'll write this up as a sort of formal step thing and summarize it later. So we're going to concentrate on this reduced one. We're going to factor the denominator. Now, this isn't an easy thing sometimes. If it's a quadratic, you try to use the quadratic formula, or just factor it, or complete the square. You've got multiple methods there. If it's a cubic, you might have to guess a root. That can be tricky. If it's higher degree still, who knows? In principle, everything can be factored down to quadratics and linear factors, but in practice, this is sometimes difficult, to say the least. So hopefully, in any problems you get asked, in this course at least, Math 104, or any sort of calculus course in college, for those of you watching online, hopefully you'll be able to factor it. So that's the next sort of thing you want to do. Now here's the critical thing. What we're going to do is we're going to bust this integrand up into a whole bunch of pieces. And to know what the pieces are, you have to know the form. There is a form of the solution, and that is based on the denominator. Not the numerator. It's based on the denominator. And there are some simple rules. There are some simple rules for what to do depending on what the factors are. What I'm going to do is tell you the rules, and then I'm going to show you this example and then one other sort of example of how to find the form. Okay, so here are rules for the form. So it depends on what the factors of the denominator are. So if a factor of the denominator is a linear function like x plus a, then form contains a term like a over x plus a. So what do I mean by this? Well, I mean, if there is a factor, x plus a, you have to write down capital A or some other capital letter, and I'll tell you how to decide this in a few seconds, divided by this linear term, x plus a. So just go with it for a little bit, and we'll see where it leads. What if you have a square, like x plus a all squared? Well, then the terms that you get are going to be something like this. A over x plus a all squared plus b over x plus a. The next common one is to have a quadratic factor. Now, some quadratics, as you know, you can factor. And if you could factor them, you'd be getting linear factors like this. But other quadratics cannot be factored, and it all depends on the discriminant. And when I write this down, I mean non-factorable. I don't know if that's a word. Factorable, factorizable, non-fact, who knows? You know what I mean. I.e. discriminant is less than 0. That's the same thing. In that case, the form looks like ax plus b over this quadratic. And those are the most common cases of what can occur. Two other cases that I've seen occur, at least in Math 104 exams, is x plus a all cubed. That's just riffing on this one up here. You have a term a over x plus a all cubed plus b over x plus a all squared plus c over x plus a. And actually, if you had a fourth power, then you'd have 4 terms. You just go down the powers, starting at the fourth power, cube, square, and the linear thing. And of course, fifth power, sixth power, well, unrealistic given the amount of time you actually have in an exam to solve one of these things, but you know, you can see what the pattern is. The only thing I haven't covered, and I haven't mentioned it in the book either, is what to do about a square of a quadratic if that whole thing is all squared. That's not in the Math 104 syllabus. The problem is integrating those things becomes very difficult. But there is a way to do it. I thought I would just mention this. Okay, so let's just see what this all means. First of all, the comment is you don't reuse letters. Keep advancing letters. So for example, let's take a look at x plus 2 over x squared minus 1. First, you can factor the denominator. The numerator doesn't matter for the form, at least. The denominator factors into x minus 1, x plus 1. So there's 2 linear factors. According to the table, if there's a linear factor, x minus 1, well, that contributes a term like a over x minus 1. Now, there's another linear factor, x plus 1. So I should write down a over x plus 1, but I can't reuse my letters. I have to keep advancing through the letters. So I'm going to take b over x plus 1, and I'll just add the 2 terms together. So that's the form for that particular solution. Now, I haven't said what we're going to do with the form yet. I will say this imminently. I'm just saying you can more or less look at the denominator and then construct the form. Now, as another example, this is a bit of a nasty one. What would the form... So if we were dealing with the following. X minus 1, this is on the denominator. X plus 4 all squared. No, all cubed, I believe. This is all in section 18.3 of Calculus Lifesaver, by the way. I should have said that earlier. So we have x plus 4 all cubed, x squared plus 4x plus 7 times 3x cubed minus x plus 1. I think that's what I wrote. Since I have the book right here for the first time ever, I can actually look it up. I like to try to be consistent. It is a cube. How about that? And what's on the top? Who cares? Junk. Anything. what would the form be? I'm going to start it here, and I'll probably need to work further down. Well, look, there's an x minus 1, so that's a linear factor. So I'll take a over x minus 1. There's also x plus 4 all cubed, so according to the table I wrote up before, I need 3 terms. An x minus 1 all cubed, an x minus 1 all squared, and an x minus 1. And notice that I started with b. So I went b, c, d. Now what about this quadratic? Well, maybe you could factor it. Let's just check the discriminant. B squared minus 4ac is 16 minus 28. That's negative. And we'll check this one where we're at it. 1 minus 4 times 3 times 1. Yeah, that's negative as well. So they're both irreducible. This one is going to give me ex plus f over x squared plus 4x plus 7. And the other one is going to give me gx plus h over 3x cubed minus x plus 1. Now that's a tremendously nasty example. Question down here first. I'm going to work my way back up, so go ahead. Oh, well, there is no good reason. The reason is that I am just confused. It should be x plus 4. What can I say? I've had a long day. How's that for a reason? Sorry about that. Yes, please change that x minus 1 to x plus 4. And while we're correcting errors, if you happen to be looking at the Calculus Lifesaver, I found the first error in it. It's probably the first of many. On page 400, after it says, and this is in this section, 18.3, where it says, so we write x plus 1 over x squared minus 1. It should say x plus 2 over x squared minus 1. So I can't work out my constants, I'm sorry. Was that what you guys were going to say as well? Okay, thank you. Right, so yes, x plus 4, powers of that on the denominator. Okay, so we have, oh, another question?
I get the concept behind x plus a squared equals a over x plus a squared plus b over x squared. Like the concept for the non-factorable guy, like ax plus b over x squared plus a. I'm confused about how that algebra is.
Okay, so the question is, how do you justify the quadratic algebraically? Let me postpone that a little bit because I want to say what the form is used for, and then I'll sort of make some remarks about that. Okay? But it's a good question. In fact, I'm actually not really going to answer it because it's too theoretical. Basically, the question is, why does this work? Let me say what this is first, and then I will say about why I'm not really going to tell you why it works. Higher mathematics is basically the answer. Go to math grad school. It's a bit of a cop-out. Okay, quick question. Oh man, what am I doing? What am I doing? This is no good. Surely I don't have a cubic. I can't even copy from my own notes. I might have to go and run and hide behind the lectern again. This was supposed to be a quadratic. Now what if this were a cubic? I'm afraid if this were a cubic, the method doesn't work. You need to factor all your cubics. This only works down with linear and quadratic factors and powers of them. Any cubic can actually be factored into a linear and a quadratic, and maybe 3 linear factors. Why is that? Cubics look like this. Or maybe like this. There's a bunch of different shapes they can have, but I'll tell you what, they all cross the x-axis somewhere. You can't draw a cubic without crossing the x-axis. That's an intermediate value theorem type of issue. So as it turns out, every cubic has a real root, and if it has a root, then it has a linear factor, x minus alpha, if alpha is the root. So the idea is that you should have eliminated all cubics in the factoring step. Anything that's left has to be linear and quadratic. So when I wrote this down, I wasn't trying to be tricky. I mean, I wrote it down wrong on my page. I can't tell the difference between my 3s and 2s on the notes. So I apologize for that. This was supposed to be a quadratic, and therefore it's a quadratic. I don't think I made that mistake in the book, though. I'm going to try to be more careful. Maybe I can meditate for a few seconds. All right. Now, why does the form work? What are we even going to do with it? Let's look back at this example, x plus 2 over x squared minus 1. We decided that the form, based on the denominator being factored, we decided that the form was a over x minus 1 plus b over x plus 1. What are we going to do with that form? We are going to set it equal to the integrand. We're going to just say that's true. Now, of course, it's not very precise. There are these two numbers, a and b, which we don't know. So the next step is to find these numbers. That's what we have to do. We have to find all these constants that pop up. By the way, one thing about the constants, I've told you, use the letters A, B, C, and don't recycle them. I've seen some textbooks, I don't believe the one for this course, although I forget, I've seen some textbooks, nevertheless, that insist on using letters like, or variables like C1, C2, C3. I don't think that's a good idea, because it becomes hard to tell the difference between them. You saw that I couldn't even read my writing on my notes and tell the difference between a 2 or a 3. When you have lots of these C1, C2, C3s floating around, it's really easy to mix them up. So that's why I prefer the capital letters. They're easier to tell apart. That's just a silly little thing, but nevertheless, it's a cry and shame to get these things wrong just because you can't tell your variables apart. So that's a bit of a word of caution. In order to get this, first of all, multiply through by the denominator. And for this, it might help to mentally, or just write it down as the factored version, and then multiply through by it. What you will get on the left is just x plus 2. And because of the way the form is constructed, on the right, the denominators will all go away. That's very important. Notice that every denominator in every piece of form is the same as one of the factors. And so when you multiply through, for example, x minus 1, x plus 1 kills off the x minus 1. And you're left with a and the other factor, x plus 1. And similarly, the b piece, the x plus 1 gets killed by that factor when you multiply it through, and you just get the other factor. And so if this is true, then this is going to be true, and vice versa. Okay, well, we've gotten rid of the fractions now. So what do we do next? There's actually two methods for finding out what a and b are, or what the constants are in general. And it's a nice sort of thing, because there are two methods, and you can actually use them both. So let me tell you what the methods are. First method, you could substitute a clever value of x. See, this is supposed to be true for every value of x. So it's got to be true for any particular value of x. So method A, plug in a clever value of x. So what do I mean by clever value? What I mean is, maybe there's an obvious x that's going to make everything simpler. And in this case, suppose you plug in x equals 1. That's going to kill off this b term, because you get b times 0. So if we plug in x equals 1, this says that 1 plus 2, which is 3, now that I'm in my meditative state, I am aware that 1 plus 2 is in fact 3, and probably will not get that wrong. The other one is a times 1 plus 1. Again, I know that's 2, so you get 2a, and the b goes away. So immediately we know that a is 3/2. Another clever value. Can anyone in here tell me what is another clever value? Minus 1. That's because that kills off this first term. If you plug in x equals minus 1, you get minus 1 plus 2 is 1, equals 0 there, and you get minus 2b. So b is negative 1/2. And we found what a and b are. Now notice that we used the method twice. We plugged in two different values. But there were two constants that we didn't know, and we found them both. Okay. Let's pretend we hadn't done that. I'll show you the other method. The other method is to equate coefficients of a power of x. So let's write down that original equation just for reference. We're trying to find x plus 2 is a, x plus 1 plus b, x minus 1. We're trying to find the a and the b that make that work. So what you could do is equate, for example, coefficients of x to the power of 1. That's just the coefficient of x on both sides. Now what you could do is expand it out, but I kind of think that it's easier in a way to just spot what's going on. So here, the coefficient of x is 1. Here we get an a and a b if you were to multiply that out. So that gives you one equation. You could also equate the coefficients of x to the 0, which is the constant coefficient. Here it's 2, and there it's a minus b. So there's a certain art to doing this. I mean, if you liked, you could write this out as ax plus bx plus a minus b, and then actually write it explicitly as a plus b x plus a minus b. And that's the coefficient of x, and this is the constant coefficient. But as I say, you can sort of just see it mentally. Now we have two equations for two unknowns, but we have to solve them simultaneously. So one thing we could do is add them up, and you'll get 3 equals 2a. Therefore, a is 3/2. And now plug that into either of those equations. Say here you'll find that a plus 3/2 is 1. B plus 3/2 is 1, and therefore b is minus 1/2. And thank goodness it's the same solution as before. Yes, a question?
Are there any problems where we won't be able to use one of the methods, which is why it's both?
No. The question was, is there any problem where you couldn't use one of the methods, as it were? And here's the deal with that. This method always works. Because you are dealing, if you've got the form right, you are dealing with the same number of coefficients as the degree plus 1. In this case, you see the degree on all sides, the highest degree floating around is 1. And we have two coefficients. Now this actually goes to your question. If you look over here, why does the form for a quadratic, your question, why is it ax plus b over x squared plus ax plus b? I say that you have two undetermined coefficients because you basically have a quadratic that comes along. So you notice that for every degree of the original denominator, you have one constant. In this case, we have degree 1, 3, 5, 7. And here we have 8 independent constants, one more than the degree. Right? A degree 7 polynomial actually has 8 constants involved. And so you definitely need two different unknowns for this to possibly work, to have enough degrees of freedom to solve this sort of equation. And the general linear factor, I mean, it has to be a polynomial type of thing, so it pretty much has to be linear. But why does this always work? That's a good question. And you typically learn this in a first-year graduate course on algebra, maybe even second-year graduate course. So the fact that it always works is a sort of nice thing, but you're just going to have to take it, I'm afraid, as given that this is always going to work if you don't make a mistake. Now, the other question, to go back to your question, what do we do here with these methods? The aim here, I need to say one more thing about the methods before I can answer the question. And that is, notice that we used, in the first one, we used method A twice. In the second one, we used method B twice. but you can mix and match. You can do one of A and you can do one of B in this case. I mean method A and method B, not constant A and constant B. So you can actually mix and match. For example, if you had found that, say, 1 is A plus B, and then plugged in, say, x equals 1, you would know what A was, and then you could use the other equation. Now, to again go back to your question, this first method A doesn't work unless you have linear factors. Right? If you have a quadratic factor up there, there's nothing clever you can put in. Of course, you can put in any values you like and get different equations. But in terms of clever values that kill off terms, it doesn't always work. It works in this case both times because you have two linear factors. So here is my guiding principle if you have to decide which method to use. Do all the clever values you can first. And then if you found all the constants, great. If you don't have enough, try the coefficients method. Okay? I'm going to do another example imminently. Another question. Is there a way you can solve these equations using matrices? The answer, of course, is yes. Whenever you have any simultaneous linear equations, you can convert them into matrices. Unfortunately, matrices is not until linear algebra, which is sort of normally a sophomore level course, so I cannot assume that anyone here actually knows them. And in any case, hopefully, nothing that you actually have to solve, at least in Math 104, will be complicated enough to require matrices. Normally, you can just solve the simultaneous equations by elementary methods. By which I mean, you won't get 8 constants. You'll get 2 or 3 or maybe 4 if you're unlucky. All right? Another question. Okay. The question was, go over again how you got these two equations. Do you see how I got this, at least? So we start off with this. Now, what I'm interested in is I want x plus 2, which is a polynomial in this case of degree 1, to always be equal to this right-hand side, no matter what value of x. So actually, do you see how I expanded it out here and then factored it? Okay, so we'll concentrate on this for a second. This is supposed to be x plus 2, which I've just transferred the right-hand side. And I'm going to even put 1x plus 2, because that's the same as 1. So here I have 1x plus 2 equals something x plus something else. And these are supposed to be exactly the same polynomial on both sides. So the only way that can be true is if the 1 equals the a plus b, and the 2 equals the a minus b. If that's the case, if I can find numbers a and b that make that work, then when you plug them in, you will in fact get 1x plus 2. And so I copied this down, 1 equals a plus b, and 2 equals a minus b. Okay? And then you solve them, and you find a is 3/2 and b is minus 1/2. Now, if you go back and plug those into this, you will find that it works, unless you made a mistake, or I made a mistake. I didn't make a mistake this time. In fact, I did it 2 ways, and it came out the same. So I could have been wrong twice, or I could have been right twice. Okay, so that's how this works. Now, that's, as I say, this is the equating coefficients method. Does that also satisfy you in terms of going over it again? Is there anyone who has any qualms about this? This is a sort of thing where practice makes perfect. I cannot stress this enough. You just need to eventually, not right now, because I'm going to say a few more things, but you need to practice a lot of these. Okay, so the point is, I'm not telling you why this works, but I'm telling you that if you do the form correctly, so if you've already factored it, and you get the right form following those principles, and you multiply it out properly and get a polynomial, which was the numerator actually. Notice this x plus 2 was the numerator. So that didn't affect how you chose the form, but it definitely affects the rest of it, as in what are these constants. So you should have the numerator equals some sort of polynomial. And then by enough clever substitutions and or equating coefficients, and you have to do one copy of one of the methods for each constant. So in this case, we have a and b. We either have to do this method a twice, the second method twice, or one of each. As long as you do that and then solve the equation simultaneously, you will find all the constants. And I cannot tell you why, and I apologize. You have to just take it from me that it will work. If you try enough of them, you'll become convinced, but that's not a proof. Math is not. You can't convince someone by saying, well, just do it. Every right-angle triangle, the sum of the squares of the shorter sides is equal to the square of the hypotenuse. Go on, draw 5 right-angle triangles and you believe me. No, you need proofs, and I'm not going to give you one. In any case, with that omission, let me just tell you what to do when you found these things. Go back up to the equation, which is unfortunately right at the top of the board here. Maybe we could just look at it for a second. We now know what A and B are. So rewrite that equation. X plus 2 over x squared minus 1 equals A, which we now know is 3/2. I'm going to stick it on the top there. 3/2 over x minus 1 plus B, I'll write as minus 1/2 over x minus 1. Plus 1, thank you. That one was a really small mistake, so I don't think it counts. Right, so now what are we going to do? Well, we want to integrate this. So let's just integrate these two pieces. Not bad. Now you see what we've done. We've busted up a more complicated expression into two easy pieces. And the reason I like to write the constants up the top and even preserve the plus, although it doesn't really matter, is you can sort of mentally or explicitly pull them out of the integral and just get 3/2 integral 1 over x plus 1 minus 1/2 integral 1 over x plus 1 dx. Now I'm going to discuss imminently how to actually do these sorts of integrals, but these ones are easy enough that we can just write this down. The integral of 1 over x is log absolute value of x. The derivative here, x minus 1, the derivative of that is 1 again. So you don't even really need to do a substitution. If you did, you'd set t equals x minus 1, but dt is just dx. So any way you look at it, this is going to be 3/2 log absolute value x minus 1. And similarly, this is going to be minus 1/2 log absolute value x plus 1, plus a constant. And now I'm not going to write it out, but if you go back to our original integral, we also had, I believe, a 5x term added to that. So this is the integral I started with. So you can write down what the final integral is. It's 5x plus this chunk here. So look back and do that. I'm leaving that to you as an exercise, although there's nothing to do other than look back in your notes. Okay, so basically, so far what we've talked about is splitting things up and getting it into the pieces. Now, we've got to do some calculus. There's a bit. Let's do some more. As I said, I'm going to do a big example of the whole method. In fact, I'm going to summarize the method and then do a big example. Admittedly, I'm doing this somewhat quickly. Haven't done a huge number of examples here of the method, but as I say, the big example will take quite a while. All right. So, just to recap, we've taken our rational function and we've busted it up into expressions like the ones that appear in the form. Okay? What are the sorts of things that can appear in the form? Well, one of them looks like this. Constant a over x plus a. That's exactly like both the terms that we just had in the previous example. But as I said, that's pretty straightforward. That's just log of the bottom plus a constant. What are the other things that can come up in a form? Well, you could have a square on the bottom. Before I even do the square, let's just worry about what happens if perhaps it's not monic. I don't know, maybe you factored it like this. 1 over 4x minus 3 dx. The 4 is not really a big deal. If it's there, you do have to be careful. You'd like to say it's log of 4x minus 3. But unfortunately, if you differentiate this, you're going to spit out a factor of 4. You're going to get 4 over 4x minus 3. So you need to compensate by the quarter there. If you don't believe it, substitute t equals 4x minus 3. Okay, so these sorts of things are quite easy. How about a power on the bottom? Suppose you have 1 over x plus 5 all squared. How do you integrate that? Well, I mean, how do you integrate this? 1 over x squared. Maybe you know the answer. After all, the derivative of 1 over x is negative 1 over x squared. So I like to be able to just write down that particular one because it's quite common. Negative 1 over x plus c. But if you don't believe it, you can also write this as x to the minus 2, and then just apply the rule. You add 1, x to the minus 1 over minus 1. So you add 1 to the index and then divide by the same thing. And of course, this is the same as negative 1 over x plus c. So if you can do that, then you can do this, because adding the 5 makes no difference to the derivative. And so this is going to be negative 1 over x plus 5. The same sort of technique works if you happen to have a cubic. For example, if you wanted to integrate x minus 7 all cubed, just write this as x minus 7 to the power minus 3, and then write it as x minus 7 minus 2 over minus 2 plus a constant, and you can tidy this up as negative 1 over 2 x minus 7 all squared plus a constant. So the linear stuff is actually pretty easy, even if you have a power of the linear. Even if you have a coefficient in the front, it's just going to spit out one factor on the bottom, like in this case, the 4. The tricky one is where you happen to have the quadratic on the bottom. So I need to spend some time talking about how to integrate this sort of form. This was one of the possibilities. ax plus b, capital AX plus capital B, over x squared plus little ax plus little b. That was a potential member of the form, although we didn't see it in the previous example. We certainly will in the big example I'm going to do. Okay, this is the last possible piece that I had given you out of the 5 possibilities that I'd written up before. 4 of them are just powers of linear, so they're easy. This one is the tricky one. Okay, to set the scene, I do have to remind you about one thing. For this to even come up, this has to be non-factorable. And remember, that means the discriminant, which in this case is not actually b squared minus 4ac, unfortunately, because I decided to call it a here and b, so in this case it would be a squared minus 4b, is negative. Okay, just to put this in perspective, if you look at this example here, that doesn't count as the sort of integral I'm trying to do, because the x squared minus 1 does factor. So you should have busted it up into these 2 pieces with linear things before you integrate. It's a mistake to not do that. So if you're going to do what I'm about to talk about, make sure that you cannot factor this denominator first. If you can, don't do what I'm about to say. Instead, do what I already said. Okay, so you have to be really alert when it comes to quadratics. If you can factor them, then bust up. You should have done that in the form first. So you only get to this sort of integral when one of the terms in the form is a quadratic like this that cannot be reduced. Now that said, I've seen problems which you start right here. You don't even have to worry about a form. This is the form. So this is part of why the topic is tricky. I'm going to, as I say, give you a 6-step method of which this is the 6th step, so we've already done all the steps. But sometimes you have to start at step 1 and do all 6 steps, and sometimes you just have to start at step 6. It's sort of weird. It's not an easy thing. But in any case, let's then just focus on how to integrate something like this. It's a linear over a quadratic where the quadratic cannot be factored. And this sort of has its own method, as it were. So I'm going to use, as an example along the way, x plus 8 over x squared plus 6x plus 13 dx. So imagine that was the problem. Let's look at the bottom. It's a quadratic. What's its discriminant? B squared. Well, I say B squared. It's just this coefficient minus 4 times this. Unfortunately, as I say, I called it A and B. But this minus 4 times this. So it's 6 squared is 36 minus 4 13s. 36 minus 52. 4 13s are 52, right? There's 13 cards in a suit, 4 suits, 52 cards in a deck. Well, anyway. 4 13s, 52 away from 36 is certainly negative. So yes, this cannot be factored, and this is fair game. By the way, if you were going through the whole steps, you would say, oh, the degree of the bottom is indeed 2. That's bigger than the top. So we skipped the long division. Remember that at the beginning, the long division? You don't have to do it. So factor the denominator. You can't. Form. Well, the form would be ax plus b over this, but there's no point in doing it because you would just get this back. There's nothing to bust it up into. It is its own form. And therefore, we just fall straight down into this method that I'm going to describe now. How on earth do you integrate this? First thing to do is to complete the square on the bottom. Now, you've all learnt how to complete the square. Please try to remember it, or at least jog your memory. I know it's been a while since you've done it, probably. Let me show you what I think is the best way to complete the square. So let's take a side sort of panel here. We take the denominator, x squared plus 6x plus 13, and we write it as x squared plus 6x plus something. We're going to fill in that something. And then we're going to subtract away that something again and add 13. So can you see that if I put the same number in both of these, this will be true? Because we're just adding it and subtracting it. So what number do you put in? Well, you take this coefficient 6 and you take half of it. You take half of it. 3. Then you square it. 9. That's the number you put. So you take half, then square. And then you put it there and there. What on earth does that do? Well, these 3 pieces factor into x plus 3 all squared. The 3 was the thing that was half of that. It was a sort of mid-step. And then these 2 you just have to work out. 13 minus 9 is 4. That's how you complete the square. This only works, by the way, if this is a monic quadratic. The coefficient of the x squared is just 1. If it's not, so if I had, for example, 5x squared there, I would just pull out the 5 out of the integral. So it's not really relevant to this example, but since I don't think I have an example of this, I just thought I should mention that, well, if I had x minus 8 over, say, 5x squared plus 6x plus 13, if that's what I had, The discriminant is still negative, as you can just check. So what I would do is first of all pull out 1/5. This becomes quite messy, so I'm not going to complete it. But I would have x squared plus 6/5 x plus 13/5 dx. Well, I just magically put it there. Who's asking me, sorry? Yes. So I notice that I don't have an x squared. I have a 5x squared. So I pull out a factor of 5, but then to compensate, I have to fix up the other coefficients by dividing by 5. So if you notice, if you were to pull in that 5, you would get 5x squared plus 6x plus 13, and you would regenerate the original integral. So you see how I've pulled out the factor of 5 from the entire denominator? Because now this is monic. This is just x squared. And so my template says I want to deal with an x squared. Okay, it's to me, this is what I would do first to get rid of any coefficient. It's not the only way to do it, but completing the square is much, much easier. The whole thing is much easier if you just pull out the factor and then worry about it at the end. Okay, so that's a sort of aside. Yeah, another question.
Where pulling out the factor is because it's easier, or because there is no other way to do it?
It's easier. It's easier. Yes.
You can solve it normally, then do it normally.
Hey, this is not the only way to do the integrals. There's many, many different ways of doing it. Even this method of completing the square first, you know, when I was originally taught this, I believe we were supposed to complete the square later in the process. By the way, I teach methods that I think are the easiest for you to do. They are not the only methods, and sometimes they may conflict with your teacher. I should take this as a given disclaimer. I think I said something in the book about it. I mean, the fact is, there's many ways to skin these cats, right? And, oh, it's pretty gory. Okay, you know what I mean. None of you actually own any cats. I like cats. Not the musical. Now, there's many ways of doing these problems, right? And what I'm showing you is what I think is the easiest, as I say. To me, completing a square, dealing with this whole method, works really nice if I don't have a coefficient in front of the x. And because I can always pull out any coefficient I have, and then it's just a constant, so it goes out of the integral, so that I can just work this out and worry about it later, I think is the easiest way to do it. But if you can do it by some method where every step is justified from the previous and get the right answer, then it's fine by me. I'm not grading your paper, though. So. I mean, I don't grade anyone's paper here, and I'm certainly not grading your papers, so I can't promise anything. But I do at least hopefully guarantee that what I do is a correct method. It's not the only one. Okay. Anyway, if you have a monic one, great. Otherwise, pull it out. If you do, well, when you've reduced it to monic, complete the square using this methodology. And then rewrite the integral with the square completed. So in this case, you get the integral of x plus 8 over x plus 3 all squared plus 4. Again, we haven't done any calculus. This is just pure algebra so far. Now, let's do a substitution. Let's put t equal x plus 3. So that dt is dx. What does this integral become? Well, we need one more piece of working here. If t is x plus 3, then x is t minus 3. So let's change every bit of this equation into t land. X is t minus 3. 8 is still 8. X plus 3 is t squared, of course, plus 4, and dx is just dt. So we have substituted our way. I'm running out of room over there, so let's just do this. Let's just rewrite that last integral. We'll just have to follow from one board to the next. It'd be nice on the videos if we could just cut all this part, but I keep on talking, so screw that. Okay, the last integral we had works out to be t squared plus t plus 5 over t squared plus 4. Okay, so the whole goal of this exercise is to get rid of the linear term on the bottom. We no longer have a linear term. It's just t squared plus something. It's not t squared minus something. If you ever do this and get t squared minus 4, say, then you're not lost, but you should have factored the original. You see, t squared minus 4 would factor, and that would mean the original quadratic would have factored. So you probably should have done that first. But you're not actually screwed if you're there. You could factor it and continue and then resubstitute. So that would be a different method along the lines of your question. In any case, once you've got it down to here, it's not too bad. You can split this up into two integrals. T over t squared plus 4 and 5, which I'm going to pull out of the integral, times the integral of 1 over t squared plus 4. Okay, so we've got two integrals. Let's do them one at a time. This one, what's the derivative of the bottom? T squared plus 4. 2t. What have we got on the top? T. What do we wish we had on the top? Okay, so let's do it. Okay, we've got to put a half there to compensate. That's the oldest trick in the book. Actually, it's not really, but I told it to you last week, and it comes in really handy. Saves you a substitution. So actually, this is just 1/2 the logarithm of t squared plus 4. Technically absolute values, but because t squared plus 4 is always positive, you actually don't need them, and it's classier not to have them. Oh, class is important sometimes. Classiness, anyway. Okay, so it's 1/2 log t squared plus 4. The other piece, it's 5 times something. What is it? Well, for the purposes of partial fractions, I want you to memorize something that we can check and you can derive, but to be sensible about it, if you just learn this really common integral here, dt over t squared plus a squared. If this a is a 1, what is that integral? Inverse tan of t. So this is very similar to inverse tan of t. It's actually inverse tan t over a with a compensating 1 over a out the front. And that comes in handy all the time in these partial fractions questions, because you often get a situation like this. So if you can just remember this. Now, why is this true? Well, the best way to see why it's true is just to differentiate this. If you were to differentiate the right-hand side, this is just an aside, by the way. You don't actually have to know this, although I would hope that you could also do it. If you were to differentiate this, you would get 1 over a as the factor, and then inverse tan is going to give you 1 over 1 plus t over a all squared. But the derivative is going to give you another 1 over a. And so if you expand this, you actually have an a squared there, and you have a 1 plus t squared over a squared. So you will get a squared plus t squared, which is exactly the denominator there. I'm not writing down the details, because you should really try to do it yourself, but it's just a simple exercise to justify this formula, which you can more or less write down. In fact, you can write it down. In this case, the square root of 4 is 2, so I simply write down 1/2 inverse tan t over 2 plus a constant. And don't forget the factor of 5 that's out the front there. So we've split it up into two pieces. The first piece we did the multiplying by 2 and dividing by 2 trick, which you can do every time. And the second piece, you use the box formula, which again, you should do every time.
What if a was like 3?
If a was 3, then I'm afraid you would need a square root of 3 there and there.
So that's how you would solve it?
Yep. If a was the square root of 3, is root 3. The square root of 4 is 2. Put down whatever the square root is. It's nicer when you don't have to use the square root sign, but it is not wrong when you do have to. On the other hand, if you had t squared minus 4 and you attempt to take the square root of negative 4, you will not be very happy. You will have to use complex numbers, and that will be a mess. You don't want to do that. Then your answer would be arctan of an imaginary number times t. Forget that. We're not doing complex numbers until the end of the semester. And even then, we're not going to do this sort of integral with them. Okay, so basically, yes, whatever it is, t squared plus something, you take the square root of that something, and you stick it here and here. Okay? We're not done with the question, though, because we're still in t land. The last thing you have to do is go back to x land using the substitution again, t equals x plus 3. So since t equals x plus 3, we get 1/2 log x plus 3 all squared plus 4 plus 5/2 inverse tan x plus 3 over 2 plus a constant. And we're almost done. The only thing left is to expand this. Now, you could just expand it and simplify it. But you don't really have to because you've already done it. Let's look back over here where we completed the square. If you've done it correctly, you should get the same thing, or a multiple of that. X plus 3 all squared plus 4 is just our original denominator. So, without actually recalculating it, we know that it's the original denominator. And then I'll just copy out the other term again to get the final answer to the problem. How about that?
So if you put your final answer as one right above that wouldn't be incorrect for like...
Well, you're supposed to simplify your answer, right? To me, this is almost simplified. I mean, call it a 9 out of 10 or a 9.5 out of 10, or possibly a rounded up 10 out of 10. But you should really leave it in that sort of simplified form. On the other hand, if you leave it in T land, that's 8 out of 10. Probably. Depends on the grading scheme, but that's a rough sort of guide. 9 out of 10 at most. You've still done a lot of work to get to that point. But still, yes, that's the answer that you would like to give. Of course, you can write arctan instead of tan inverse if you like. That's the same thing, but that's not materially different. Okay, so in any case, though, this to me is the best method. So let's review what we did once again, because these steps are the same for all these problems. This is not a special example. This is a generic example. Right? It's about these problems are all the same. That's what I'm trying to say. You could write down any linear function divided by any quadratic with negative discriminant and solve it. You don't even need to look up a source of exercises. The only reason to do an exercise from a book instead of one that you can write down by picking 4 random numbers and hoping, adjusting them if the discriminant is negative. The only difference is that the numbers work out more nicely in this problem. You don't have square roots of 3. Everything is just whole numbers. Question? Integrals in general.
Over e squared over plus a squared?
Yes, this integral over here.
Why can't you just look at this as natural log of e squared plus a squared, then divide it by the derivative of the denominator?
So you want to know, why is this not equal to natural log of t squared plus a squared over, say, 2t or something? And the answer is that if you differentiate that, you have to use the quotient rule. And you will not get this. Yeah, you will have a mess.
So what's the rule?
There's no rule for integrals. There's a whole lot of different rules for integrals. They're tricky. Derivatives is much more straightforward. Integrals, the only rules involve undoing derivatives. So you have, so far, the basic, do I see an antiderivative? Substitution. Integration by parts. And now this partial fraction method. Next time we're going to do trig substitution, and that's actually the final method that we're doing. Everything else so far is just that sort of thing with tricks. This actually you can do by substitution. If you want to, you let, say, t equals u times a times u, where u is the new variable. And then it will work by substitution. But I elected to verify the formula instead by differentiating the right-hand side. So this is a substitution integral, and it reduces to an antiderivative that we know, which is t squared plus 1. Another question?
Would you use the integral of something where the denominator at the top equals the denominator at the bottom?
The derivative of the top?
I'm sorry, the power of the top, the power of the top equals the power of the bottom.
You mean the degree of the top?
Degree, sorry. Yeah,
Okay.
Degree, sorry. X squared plus 4 over x squared plus 3x equals 2.
So your question is, if you had something like x squared plus 4 over x squared plus 3x plus 2. Okay, to do that, the first thing I would do is, as I said, is a long division. Now, if you like, what I will do is come back and do this example for you before, after I've done my big example in the method. Okay? Can you remind me what it is, though, in case I erase it, which I probably will? The thing is, yes, here you've got to first start off by doing the division. And even after that's true, I believe this factors into x plus 2, x plus 1. So you're not even going to use this method. It's more like the previous example I did with the x squared minus 1 on the denominator. So that's not even an example of this type. Okay, just to review the steps in this last little section that I've been talking about, how to deal with a linear over a quadratic. Let's go back at this and look at what we did. The first thing, I guess, although it wasn't in the same example, is if it wasn't monic, we made it monic, the denominator, by pulling out the factor and getting other things here. Now, as it turns out, that's a real messy thing here, but you could still complete the square using the method. Yuck. So instead, I say, okay, let's suppose it actually looks like this, and it is monic. Step 1, complete the square and write it up there. Step 2, substitute t for the bit that is inside the square to get it down simpler. It gets down to something like this. It'll just be something t plus something over t squared plus something. Now split it up into the t. You can always throw the constants out the front, remember, like I did with the 5 here. Although we don't have a constant in front of the t, so it didn't apply in this case. But I put in the 2 and the half. That's just a good technique so that I can say it as a half log whatever the bottom is. For the other integral, it's just this inverse tan using the formula. You don't always get 2 integrals. You might just end up with 5 over t squared plus 4, in which case you only have the second integral. Or you might end up with t over t squared plus 4, in which case you only have the first integral. But that's all you can get. As I say, it looks tricky, but if you do 4 or 5 of them, you'll see they're all the same. They're all the same. They just have different numbers. Okay? So you've now seen everything. You've seen the whole method. Unfortunately, it's probably swirling around in your mind as like what the hell is all that? How do I put it together? So what I'm going to try to do is just summarize it and remember the main points. Okay? So the first thing we did is check degrees. Is the degree of the bottom, well, let's write it like this. Is the degree of the top less than degree of the bottom? If yes, great, golden. Otherwise, which deserves a sad face, because you have to divide first. A long division. Okay, that was the first thing we did. But after you've done a long division, you get little bits popping out that are easy to integrate, like 5 or x. And the rest of what you have is nice. The degree of the top is less than the degree of the bottom. So you can go on to step 2 on that piece. So step 2, factor the denominator. You just have to pull out your techniques to do that. 3, write down the form using the rules I wrote up before. Maybe they should be part of the summary, but since I've already given them to you, they were written on the previous board there once upon a time, and hopefully in your notes and definitely in the book, then that's where you pull out that. 4. Write down the integrand, that's the integral p over x equals q over x. It's the integral without the integral dx bit, just the bit inside the integral, equals the form. After all, you're trying to bust this up into these bits. The form consists of bits. So write that down, multiply through by denominator, which is the q of x, and then use a combination of those two methods. Use a combination of method A, which was to substitute in clever values, and B, equate coefficients of a power of x and remember, you use enough of those so that you have exactly as many equations as you need. So in particular, if you have 6 constants, A, B, C, D, E, F, that you don't know, you have to do a total of 6 applications of those two methods together. You could do 6 of A, 6 of B, or any combination, 4 of A, 2 of B, whatever, in order to find your 6 equations that you need. Solve equations simultaneously to find the constants. Then rewrite the integral that you want as the integral of each piece of the form. From the form, this is from the form, each piece of the form gets a separate integral with the constants filled in. Okay, that's the big step. Step 4 is the big algebraic step. You need to find those constants, and then you need to rewrite your integral as a sum of separate, simpler integrals, one for each piece of the form. Remember, the form has constants, A, B, C, that you don't know. And so when you write down P over Q equals the form, you don't know what that is yet. You only know the template of it. You need to fill in those constants by using these simultaneous equations. After you've done that, you can write down your integral as the pieces of the form, but without the A, B, C, D. You're filling in the numbers that you've already found. The last 2 steps, then, are going to involve finding those integrals. So I'm going to write them up, and then I'm going to do a grand example showing the whole form in action. It's going to involve all 6 steps. So step 5 is going to be just integrate the linear parts. So Step 5, integrate linear terms, so linear and powers of linear, like anything that you have floating around, like dx over x plus 3, dx over, I don't know, x minus 5 all squared, etc. And that's just done essentially using the power rule, x to the a is x to the a plus 1 over a plus 1. Remember, of course, to write this as x minus 5 to the power minus 2, etc. So that's fairly straightforward. You don't really need to, that's just substitution. But you don't even need the substitution because the derivatives are the same. X plus 3 has derivative 1. So step 6, though, you integrate the quadratic denominator terms like this. Using the method we just said, first, or almost zeroth, if not monic, pull out the factor of x squared outside the integral. But that's sort of just prelim stuff. You probably should have done that before, when you factored the whole thing anyway. But basically what you want to do is complete the square on the denominator and write in the integral as, well, something. What is it? You know what? I'm sorry, I meant to write up here capital AX plus B. It works with any linear thing up there. Sorry about that. So write this as x plus alpha squared plus beta squared. That's what you should be looking for, or plus beta if you want to be more precise. That's what it looks like. Then split up into two integrals. The first one looks like, oh no, I've missed a step. I must have lost my meditation. The next step is to substitute t equals x plus alpha, whatever that happens to be, and then dt is dx. And that will reduce the integral to at plus something. I'm starting to run out of letters. Gamma. And the bottom is now t squared plus beta, whatever that happens to be. I don't want you to learn these variables. I want you to just look at them to be familiar with what these things should look like. Split into two pieces. I always pull out the constants whenever I can. The pieces, one piece should always look like integral of t over t squared plus b. And the other piece should always look like 1 over integral of t squared plus something, beta. For the first piece, use the 2 trick. 1/2, 2t, and this gives you log of the bottom. Whereas for this piece, use the formula from before, which I'll just write up again because it's in the summary. dt over t squared plus a squared. So here I'm thinking of beta, I've called it, as being a squared. So that's 1 over a inverse tan t over a plus a constant. And that you are going to memorize. Finally, back to x land. By reversing the substitution, use the completing the square formula, which you did back up there. I don't know. So look back up there and use the completing the square formula to help simplify log, if there is. So it's to simplify this first term. That, in gory detail, is the method. So, now I'm going to erase it, because I don't have enough boards. I'm going to do a pretty grand example, as I said. It's going to illustrate the whole thing, and hopefully tie it together in your minds. And then you will see that you just need to practice it, and you will turn yourself into a partial fractions computer. I really hate that sort of characterization, I'm afraid. Math is really not about computation in general, but this particular technique is just, it's just very computational, you know. It's nice to be able to do these things, but it may be, from at least your viewpoint, the least interesting part of the whole course. As I say, the theoretical underpinnings are actually quite nice, the algebra piece. But c'est la vie. So here is the example I'd like to do. And this is in section 18.3.3, if you'd like to follow along. This example is x to the fifth minus 7x to the fourth plus 19x cubed minus 10x squared minus 19x plus 18 over x to the fourth minus 5x cubed plus 9x squared dx. You have permission to barf if you desire, for it is pretty disgusting. Well, maybe not in the classroom, but if you need to excuse yourself. Yes, it's about as disgusting as you could possibly imagine in one of these exams, for Math 104 at least, but let's see how it all works. So step 1, check the degrees. The degree of the top is 5. It's not less than the degree of the bottom, 4. Even if it was equal, we'd still have to divide. So I'm afraid we have to divide x to the fourth minus 5x cubed plus 9x squared into x to the 5, and I just have to write all this out. Okay, let's do it. X to the fourth goes in a factor of x, because x times x to the fourth is x to the fifth. And you get x to the fifth minus 5x to the fourth plus 9x cubed. Take it away, and you get negative 2x to the fourth plus 10x cubed, and we'll carry the 10x squared. Okay, now we have minus 2 lots of this, x to the fourth. So let's multiply this, and you get minus 2x to the fourth plus 10x cubed minus 18x squared. And if you subtract this, you get 8x squared, and we'll just push down the 19x plus 18 because we find that the degree is now 2, which is less than the fourth. So this is just the remainder. There's no way to keep going. There's no way to keep going. I mean, how many times does x to the fourth go into x squared? Doesn't. Yes, did I make a mistake?
I think it should be
the 19 and the 9 here. So I'm subtracting this from this to get 10. And now I'm subtracting negative 18 from negative 10. So minus 10 minus 18 is 8. I think it's right. In fact, is it right? It is right. I think it's right. Okay, so the result of these shenanigans is that I can now write my original integral, and gee, I don't want to write it again. So I'm going to sort of write this over here as the quotient x minus 2 plus the remainder 8x squared minus 19x plus 18 over that horrendous denominator. Actually, it's not that horrendous. X to the fourth minus 5x cubed plus 9x squared. And this dx. And I want you to observe that in the leftover piece, the degree of the top is now less than the degree of the bottom, which is great. Okay, so you need to see how I took this division and assembled the results into the quotient plus the remainder over the denominator. That's how these things work. And the beauty of it is, you can already do some of the integral. The answer is going to be x squared over 2 minus 2x plus something. I've got to fill in that something. So I'm going to come back and fill in the final answer here. This is going to be it. Hopefully I can fit it into this space. But before, I've clearly got to focus on this new integral, which I will rewrite because I can't see that far up very often. I don't want to keep looking back up. X to the fourth minus 5x cubed plus 9x squared dx. So let's concentrate on that. Step 2 says factor the denominator. Now it's a quartic, which is normally cause for great alarm, but in this case there's an obvious factor. The denominator, x to the fourth minus 5x cubed, there's going to be a whole lot of work before I go on to the next stage, plus 9x squared factors into x squared outside of x squared minus 5x plus 9. The question is, does that need to be factored further? Well, 5 squared, or negative 5 squared, is 25 minus 36. The discriminant of this is minus 11, which is negative. So no, you cannot factor that. The discriminant is really, really useful. If it's negative, you can't factor it. If it's 0 or positive, you can factor it. If it is 0, in fact, it factors into something all squared. So the discriminant is pretty cool. What's the form of this? X squared you might think of as a quadratic. But I want you to think of it as, in this context, as x minus 0 all squared. Think of it as a power of a linear function. Because after all, x squared as a quadratic does factor into two pieces, x and x. So I want you to use this idea of saying, well, if this is x minus 3 all squared, one form would be a over x minus 3 all squared plus b over x minus 3. But it's not x minus 3, it's just x. X squared, b over x. That's what you get out of the x squared term. It's actually not wrong to put linear, but it kind of, it makes life a little more difficult. So I want you to think of this as a power of a linear function, in this case, a linear factor, in this case, x. Whereas this other piece, you get cx plus d over x squared plus 5x plus 9. That's the form. And that's supposed to be equal to the original integrand, 8x squared minus 19x plus 18 over x squared times, I'm putting the factored version because it's a little bit more straightforward. Okay, so according to step 3, then the original integrand is equal to the form. Step 3 tells you how to write the form. Okay, now here comes the fun part. Step 4 says we have to multiply through by the denominator to get an equation here. So the left-hand side will just be 8x squared minus 19x plus 18. Now we're going to play a game on the right. We need to multiply through by x squared times x squared minus 5x plus 9. The x squared is going to kill this x squared, and we will be left with, in the first term, x squared minus 5x plus 9. How about the second term? X squared kills the x, but there's still a factor of x left over in addition to the second term here. So you will get bx x squared minus 5x plus 9. And finally, the last term, x squared minus 5x plus 9 gets killed, but you now have another x squared. So you will get cx plus d times x squared. And that is the equation that you need to deal with. All right. Any questions at this point? Just to pause for breath as much as anything else. We're still about halfway through this problem. It's a long one. Okay? Well, then I'm going to keep going. As I said, there are two methods. One is to substitute clever values. Now, there's no clever value you can put in that makes this quadratic go away. There's no substitution that makes this 0. If there were, then you could have factored it, and the discriminant wouldn't be negative. So, unfortunately, it's only the linear type terms that give you something, and in this case there's only really one, the x squared. It's a power of a linear. So x equals 0 will certainly clear away some of the stuff. So let's go over here. I'm working on this, but I don't have room. I have to go up over here. So if we put in x equals 0, then you get 18 is equal to 9a, and everything else goes away. Bx, x equals 0, gone. X squared here, gone. So you get a equals 2. Unfortunately, that's the only simple value. So for the rest, I'm afraid we're going to have to resort to equating coefficients. I wish I hadn't made this arrow quite so extravagant, because I'm going to need the space. Yuck. Okay, anyway, let's equate coefficients of x cubed. Now that's a little bit tricky. Let's equate coefficients of x cubed. What's the x cubed on the left? 0. There isn't an x cubed, so the coefficient is 0. How about here? Do you get a coefficient out of a x squared 5x 9? No, no x cubes there. What about bx times x squared? That will give you bx cubed. So this will contribute a b. How about this? Cx times x squared. It will contribute a c. So that is an equation. Let's continue with the coefficient of x squared, and this will, again, give you more of a hang of what's going on. You get 8 on the left, because this is all x stuff, 8x squared. You only need the coefficients. How many x squareds do we have from here? A x squared. This could be quite hard to film. What about this? Bx cubed. How many x squareds do we have? We have a bx times negative 5x. So you've got x squared, and the coefficient will be negative 5b. So we have a minus 5b. What about, from this term, cx times x squared is already x cubed, but d times x squared will give you a d. Okay? Again, you could expand all this out and group it and just write it down. But it's good technique to try to read off the coefficients. Let's do it once more for x to the 1. See, remember, there's 4 unknowns, a, b, c, d in this problem. So we need to do 4 things. We've already done 1 clever substitution. We've got to do 3 coefficients. So the x to the 1, we have negative 19. That's the coefficient of x. Over here, we're going to get a minus 5a, because that's the coefficient of x. What about this? We're going to get bx times 9. So that will give you 9b as a coefficient. How about from here? There's no x term because you're going to get already x squared times cx and d times x squared. There's nothing smaller than x squared from there. So those are the complete set of equations. Okay, again, it's worth looking over this, trying to do it yourself, and make sure that you can. By the way, if you were to equate the constant coefficient, remember, you only need to do 4 things. Let's just, though, pretend that we also equate the constant coefficient. Here you get 18 equals, well, we're going to get 9a out of this, because that's the constant. But there's no constant here because of the x. Everything has at least an x, and here everything has at least an x squared. So you get 18 equals 9a. Does that look familiar? It's the same as what you get by plugging in x equals 0. So this is actually where the 2 methods overlap. Those 2 methods, substitute in clever values and equate coefficients. If you happen to substitute x equals 0, it's the same as equating the constant coefficient.
What's the rule?
What is the rule? Ah. Okay. He was joking. Okay. So the basic thing is that, yes, if x equals 0, that's the same as substituting in, rather equating the coefficients of x to the 0. That's where the 2 methods overlap. After all, the constant is what you get when x is 0. That's how you find the constant term. Anyway, we have to solve these equations. Luckily, it's not so bad. We know a equals 2, so if you plug that in, you get negative 19 is negative 10 plus 9b. So 9b is minus 9, and this works out as b equals minus 1. And then if you plug that in here, you'll find you get 8 equals, so in here, we'll get 8 equals, a is 2, b is minus 1, so you get 5 plus d, and we find that d equals 1. And finally, up here, b is negative 1, so c has to be 1. So we found all 4 of them. A is 2, b is negative 1, c is 1, and d is 1. I'll just underline those 4 facts. So what? Well, we can come up over here and rewrite, we replace A, B, C, and D by those numbers that we just found. So in particular, I can even do it in place up here in this integral. I'm going to get a over x squared. What was a? 2. Plus b over x. What was b? Negative 1. Plus cx plus d. What's c? c is 1. And d is 1 over x squared minus 5x plus 9 dx. And that's the result of the form. Okay, everything below this line is step 4. And that's the real key. That's the sort of algebraic meat of this subject. Let's stare at that a few seconds more as I erase this other side. Any questions about that? You can start shouting them out if you have one. I'm not going to have any time to do powers of trig functions, I'm afraid. That's okay, I'll do them next time. Okay, so let's do these integrals. The first integral is not too bad. 2 over x squared dx. As I said before, the integral of 1 over x squared is negative 1 over x. So this is going to be negative 2 over x. We also have an integral of 1 over x. Well, that's just log, and it happens to be a minus sign. But the real question is, what is this integral? X plus 1 over x squared minus 5x plus 9. And now, see, this was step 5 here. Well, I didn't label any of the steps, but in any case, this is now step 6. It's a linear function over a quadratic with negative discriminant. So let's look at that sub-method in there. What's the first thing we do? You remember? Complete the square of the bottom. Look how similar this is going to be to the other one. We complete the square. X squared minus 5x plus 9 is x squared minus 5x plus something. Subtract away the same thing and then add 9. What's that something? How do you find that? Yep, so you take minus 5, you divide by 2, and you get minus 5 halves, and then you square it. So unfortunately, you have to add in 25 over 4, which is 5 halves squared. And then you have to subtract that again. These two pieces are just x minus 5 halves all squared. And this piece, you just have to work out that, hey, 9 is 36 over 4. So 36 minus 25 is 11 over 4. So that's a bit more nasty in terms of the numbers that come out than the previous example that I did. But never mind, we can write this integral as the integral of x plus 1 over x minus 5 halves all squared plus 11 over 4 dx. Okay, what's the next step? How do you get rid of that? First, though, that's the step afterwards, split up the integral. What's the first thing to do? How do you, yeah, t equals x minus 5 halves. dt is dx, and just for reference, x is t plus 5 halves. And so this integral becomes x is t plus 5 halves plus 1 over t squared plus 11 over 4. And dx is the same as dt. Very similar to the previous problem. The only thing that I'm motivated to do is group these together and write 7 halves. Okay. So now we split this up. So this was what you thought we should do next. It would have been okay, but then you would have had to do the same substitution in 2 integrals instead of 1. Sorry? Okay. Nothing. So that also describes the quantity of chalk that I have. Here we go. Split it up. One integral is t over t squared plus 11 over 4. The other integral is 7 halves comes out times 1 over t squared plus 11 over 4 dt. In this first integral, I do the 2 1/2 trick. Now, it happened to just be t, but as I said, if for some reason I'd gotten 7t here, I would have pulled out the 7 first, and it would just be floating around. So it's always the 2 1/2 trick. You don't have to think of it as the 7 2 7, no, 7, whatever. It's just the 2 1/2. And now we can just write down the answers to both of these integrals. This is a half log of the bottom, t squared plus 11 over 4. And actually, you don't need the absolute values again, because that quantity is always positive. Plus 7 halves times something. What is that something? Well, you need to pull out that boxed integral, but unfortunately, a is going to be the square root of 11 over 2. You need to take the square root of this, and it's nasty. So the answer is 1 over the square root 11 over 2, inverse tan t over square root 11 over 2, plus c. Didn't say it was going to be nice. In fact, I think I used the word bath. 1/2. Okay, let's worry about the log thing. We've got to go back to x land. T is x minus 5 halves. So you get x minus 5 halves all squared plus 11 over 4. Flip the root 11 over 2 to be 2 over root 11. And you'll get 7 over root 11 inverse tan 2t, which is 2x minus 5 halves over root 11. And there's one more simplification. Do not try to multiply this out. Instead, look back up here and reverse the complete the square. Look, x minus 5 halves plus 11 over 4 is just x squared minus 5x plus 9. So this is 1/2 log positive quantity x squared minus 5x plus 9 plus 7 over root 11 inverse tan 2x minus 5, we can now write over root 11. There's almost nothing left. We just have to assemble the pieces. Let's go back to our original integral. Right there up the top. We already busted out an x and a minus 2, which we've integrated already. And all that was left was to fill in the answer from that integral. This is the integral that was left. There are 3 pieces. 1, 2, and 3. And we took care of all of them on the right-hand board. So now all we have to do is fill them in. And I am now going to do this. The first piece was 2 over x squared, which contributes a minus 2 over x. The second piece was negative 1 over x squared, which contributes a minus log absolute value of x. And finally, there was this quadratic piece, which contributes, and I'm just copying it from the bottom of that board over there, 1/2 log x squared minus 5x plus 9, and then plus 7 over root 11 inverse tan 2x minus 5 over root 11 plus a constant. And we're done. Okay, you, I'm afraid, are expected to be able to do this. I'm not really afraid because I know you can. I'm just afraid that I have to tell you that you're expected to do this because I know it's sort of nasty. But then again, as I say, this is the sort of thing that it's really meat and potatoes. Apologies to any vegetarians in here. The fact is, what I mean is, it's straightforward stuff. If you practice it, it's easy points. You don't have to think of something clever. You just have to do the algorithm. It's a long algorithm, but hopefully I've tried to cut it down to size a little bit. Okay, so here's the story. I don't know if you still wanted to do your example from before. We don't... Yes, you have to long divide. So, I don't know, there are probably still a few minutes left if anyone has any questions. Otherwise, next time we're going to do all sorts of trigonometric integrals, including trig substitutions. That's the plan. So, until then.